This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. The Academy of Science, to which Newton was the president of from 1703 to 1727, was formerly the Invisible College, which became the Royal Society of London for Improving Natural Knowledge, or just the Royal Society. The college and the society had Robert Boyle as a member. Boyle was the first to experimentally demonstrate the relationship between pressure and volume in gas interactions, and from his experiments created what we call Boyle's Law. Boyle's Law states, for a fixed mass of an ideal gas kept at a fixed temperature, pressure and volume are inversely proportional. V is proportional to 1 over P. P is proportional to 1 over V. P times V equals some constant. And P1, V1 should be equal to P2, V2. This makes sense. If you put gas in a box and shrink the box, but you keep the temperature the same, the pressure of the gas being squeezed will Newton's law that same amount of pushback equal to the squeeze, and the pressure increases. Reduce the squeeze, relax the box, and the pressure eases. In 1787, Jacques Charles formulates what we call Charles' Law, which states, the volume of a given mass of a dry gas is directly proportional to its absolute temperature at a constant pressure. Volume is proportional to temperature. V over T is equal to some constant, and V1 over T1 should be equal to V2 over T2. Again, this makes sense. We repeat the box squeezing experiment, but we keep the pressure constant. So, we actually don't squeeze the box. We let it move when it wants. Then, the volume and temperature increase together, as the gas will expand the size of the box as you heat it, and will shrink the box when you cool it. In 1808 we get Gay-Lussac's law, or the pressure law, by Joseph Louis Gay-Lussac, which states, the pressure exerted by a given mass and constant volume of an ideal gas on the sides of its container is directly proportional to its absolute temperature. Pressure is proportional to temperature. P over T equals some constant, and P1 over T1 should equal P2 over T2. Now if we repeat, and we prevent the box somehow from changing its size, the more you heat the box, the more pressure will build up inside the box. If you were to somehow add pressure to the box, the temperature would increase. In 1811 we get Amedeo Avogadro's law, which states, the volume occupied by an ideal gas at a constant temperature is directly proportional to the number of molecules of the gas present in the container. Volume is proportional to the number of particles. V over N is equal to some constant, and V1 over N1 should equal V2 over N2. If the volume of the box is again allowed to move when we need it to, and we put gas into the box and walk away for a while and let it settle, the final volume of the box will depend on the amount of gas in the box. Given this, it was found that since PV equals some constant, and V is proportional to T, and P is proportional to T, then the formulation can become PV equals some constant, or is equal to some constant times T. When we add in Avogadro's law, that V is also proportional to N, the formula becomes that PV is equal to a new constant times N times T. We can rewrite this as PV equals nRT, where this constant, this new constant, will be set to equal R. And R is the universal gas constant. The constant is the result of the universe, but also of the equation, as when you solve for R, you get R equals PV over NT, which can be expressed by the physical units of work per mole per degree of temperature. And the constant that pops out in that way is that R equals 8.314462618 kilogram meter squared per second per Kelvin per mole. The final formula, PV equals nRT, is called the ideal gas law equation. Simply, it says that the pressure and volume of a box depends on the number of ideal particles in the box, and the temperature of the box, and some constant of the universe. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.